Hello everyone. So today I'm going to present the topic Gauss Law applications, volume charge distribution. Here we will see the uniformly charged non-conducting cylinder. Okay, uniformly charged non-conducting cylinder, right? The plan of my talk is first let us see the introduction. After that, Gauss Law application to volume charge distribution for uniformly charged non-conducting cylinder. Then after, we will see the conclusions. So before start of this lecture, once again, I will repeat the statement of Gauss law. So what is the Gauss law, sir? The normal electric flux through over a closed surface is equal to 1 by epsilon naught times to the net charge enclosed within the surface. Mathematically, we represent it as surface integral E bar dot ds bar equal to 1 by epsilon naught times to the charge enclosed within the surface. Okay, this is integral form of Gauss law. The differential form of Gauss law stated as del bar dot E bar equal to rho by epsilon naught or del bar dot capital D bar equal to rho, where rho is volume charge density. Okay, so the normal electric flux over a closed surface is equal to 1 by epsilon naught times to the total net charge enclosed by that surface. This is the statement of Gauss law. So keep this statement in our mind. Let us see the application volume charge distribution in the case of uniformly charged non-conducting sphere. In the last class, we discussed about Gauss law application for uniformly charged conducting sphere and a non-conducting sphere. Okay, this is also volume charge distribution, right? You observe the figure here. So here I have shown yellow color cylinder. So this yellow color cylinder denotes the uniformly charged non-conducting cylinder with radius capital R, and the charge Q is distributed over throughout this volume, okay, with surface charge density sigma and volume charge density rho. Okay, అంటే ఇక్కడ ఎల్లో కలర్ లైన్ తో చూపించినటువంటి సిలిండర్ ఉంది కదా, ఇది మన యాక్చువల్ గా తీసుకున్నటువంటి సిలిండర్. దీన్ని యూనిఫామ్ గా చార్జ్ చేసామండి. దీని యొక్క రేడియస్ వచ్చేసి క్యాపిటల్ ఆర్, వాల్యూమ్ చార్జ్ డెన్సిటీ రో. ఓకే, సో క్యూ చార్జ్ త్రూఅవుట్ దిస్ వాల్యూమ్ యూనిఫామ్ గా డిస్ట్రిబ్యూట్ అయి ఉంది. ద వాల్యూమ్ చార్జ్ డెన్సిటీ ఇస్ రో. ఓకే, నౌ హియర్ by using the Gauss law, we have to find the electric field strength at the 3 different points. So this is the point P1. So I will show that. So here this is the point P1, external point, right? Now point P2 is on the surface. Next point P3 is inside the cylinder. Internal point, P1 external point, P2 surface point, P3 internal points. Okay, so we should calculate the electric field strength at the 3 different points by using the Gauss law with the concept of symmetry of charge distribution, right? So to calculate the field strength at the point P1, I constructed an orange color Gaussian cylindrical Gaussian surface. Okay, సో ఇక్కడ రెడ్ కలర్ లేదా ఆరెంజ్ కలర్ తోటి నేను ఒక గాషియన్ సిలిండ్రికల్ గాషియన్ సర్ఫేస్ ని కన్స్ట్రక్ట్ చేశాను. ఎట్ ద పాయింట్ P is at the distance R from the axis of the cylinder. సో ఇక్కడ గ్రీన్ లైన్ ఏమో సిలిండ్రికల్ యాక్సిస్ అండి. సిలిండ్రికల్ యాక్సిస్ నుంచి స్మాల్ ఆర్ డిస్టెన్స్ లో P1 అనేటువంటి పాయింట్ ఉంది. P1 వద్ద ఎలక్ట్రిక్ ఫీల్డ్ స్ట్రెంత్ ఫైండ్ అవుట్ చేయడానికి P సర్ఫేస్ మీద ఉండేటట్లుగా నేను ఒక సిలిండ్రికల్ గాషియన్ సర్ఫేస్ కన్స్ట్రక్ట్ చేశాను. Okay, so now the P1 point lies on the surface of the red color or external Gaussian cylinder. Okay, now at the point P1, again I assume a small surface area element. This is denoted by the brinjal color. So small area is the vector quantity. You know that. What is the direction of small area vector? It is outward normally. Normally outwards. It is denoted here. ds bar direction is ds bar direction denoted in upwards. But the direction of electric field strength at this point is normally outwards or radially outwards. So catch that point, radially outwards or normally outwards at every point. So here the direction E bar like this, here the direction E bar, here the direction E bar like this. The blue color lines denote the direction of electric field strength. At every point on the surface of this external cylinder, Gaussian cylinder, the direction of electric field strength is normally outwards. Now, let us discuss at the point P1, sir. At this point, the ds bar direction and electric field strength direction are in the same direction. So angle between ds bar and E bar, how much, sir? 0 degree. So what is the flux through this small area element? D phi equal to, we write E bar dot ds bar. Okay, how we write? D phi equal to E bar dot ds bar, that is called according to A bar dot B bar formula. E bar dot ds bar equal E ds cos theta. Since angle between E bar ds bar 0, here this is equal E ds cos 0. Since cos 0 equal to 1, we get E into ds. This is small area నుంచి బయటకు వచ్చేటువంటి ఫ్లక్స్. ఓకే, ఎలక్ట్రిక్ నార్మల్ ఫ్లక్స్ ద స్మాల్ ఏరియా ఎలిమెంట్ ds. But we should consider the total flux through this entire cylindrical surface. So for that, we should integrate this one. So here, for this external cylinder, we have 3 regions. So this is the circular end region, left end. This is another circular region. This is right end, circular end. The remaining part is the curved surface region. So at the left end, the direction of ds bar is perpendicular to this, that will be in this direction. ds bar direction towards left, that is denoted with brinjal color. But the direction of electric field strength is, it is in this direction, or that may be in this direction. Whatever it is, here ds bar and E bar are perpendicular. Therefore, flux through the small area element at this point, E bar dot ds bar equal to EDS cos 90, that will be 0. So what is the conclusion here? Through the left circular and electric flux 0, through the right circular and electric flux 0. That means what? No electric lines of force will move in this direction. No lines of force will pass in this direction. Only the electric lines of force will come out from the curved surface only, from this curved surface only. That is the concept. Therefore, the total electric flux through this entire outside cylindrical surface is equal, according to formula we are writing first simply, flux through the left circular end, flux through the right circular end, flux through the right curved surface region. So this is 0, it is 0. Therefore, only the flux through the curved surface is the net flux. The net flux linked with the closed surface is equal to the flux through the curved surface region only. Okay. Therefore, for this already have written for small area element d phi equal to how much we got, sir? E into ds. Therefore, the total flux through this entire curved surface is given by, we should integrate this one. So here I am showing phi is equal to integral of d phi over s, surface integral, that equals surface integral E into ds. This is substituted here. Since electric field strength at every point on the surface is constant, because every point is at the same distance from the axis of the cylinder, that is at r. Therefore, magnitude of the electric field strength at every point on the surface is constant. Since E is constant, E written outside of the integral, E into integral of surface integral ds. So what is the surface integral ds? That is the total surface area of this curved surface, that equal to 2 pi RL. The surface area of the cylinder formula, you know, 2 pi RL. Okay, this is equation 1. So this is we calculated according to the electric flux concept. Now let us apply the Gauss law. According to the statement of Gauss law, that normal flux should be equal to 1 by epsilon naught times to the charge enclosed by this Gaussian surface. So what is the charge enclosed by this external Gaussian surface? That is the charge distributed over the this non-conducting cylinder Q. So that is written here. Phi equal to Q by epsilon naught. It is equation 2. From these two equations, they can write E into 2 pi RL equal to Q by epsilon naught. Okay. So E into 2 pi RL equal to Q by epsilon naught. Therefore, you write E as the subject, then field strength at outside point equal 1 by 2 pi epsilon naught Q by LR. Here the charge distributed over the non-conducting cylinder is constant, Q constant. Length of the cylinder is constant. Epsilon naught permittivity of free space is constant. Then E out depends upon what? It is depends on distance. How it depends? It is inversely proportional to R. So for external point, field strength inversely proportional to square of the distance of that point from the axis of the cylinder, and axis నుంచి ఎంత డిస్టెన్స్ ఉందో దానికి ఇన్వర్స్లీ ప్రపోర్షనల్ గా ఉంటుంది. కాబట్టి ఎక్స్టర్నల్ పాయింట్ కి ఫీల్డ్ స్ట్రెంగ్త్ ఇట్ ఇస్ డిక్రీజింగ్ according to this formula, E inversely proportional to R. Okay. Now the point P2. The second case is we are considering the point P2 on the surface of the actual non-conducting cylinder. The actual non-conducting cylinder is shown with the yellow color line. So now the point P2 considered on the surface of the cylinder, right? So there again I consider the small surface area element. This is denoted with the brinjal color. It is ds. The direction of ds bar is it is perpendicular to this outward direction. Electric field strength is always radially outwards. So here also E bar ds bar in the same direction. Then the flux through this small area element, we write it as same. D phi equal E bar dot ds bar, that equal to E ds cos 0 equal to E into ds. So that is written here on the surface of the cylinder. So then the total flux is equal to surface integral of d phi, that equals surface integral of EDS. Again here P1, here the point P1 is on the surface of the cylinder. At every point on the surface of the cylinder, electric field strength in magnitude constant. Therefore, E written outside, integral surface integral ds. But the surface integral of ds is nothing but what? That is the total curved surface area. E into surface integral of ds, that is 2 pi Rn. Okay. So that is what I am saying. Here, the total curved surface area of this cylinder, the yellow color cylinder, how much, sir? Because its radius is capital R, then that would be 2 pi capital R L. Okay. Now that is written there. 2 pi capital R L. According to the Gauss law, phi equal to Q by epsilon naught. Here also charge enclosed with that yellow color actual cylinder is how much? That is charge on the cylinder or charge distributed over the non-conducting cylinder Q. So Q by epsilon naught. Here also Q. Equating these two, E into 2 pi RL equal to Q by epsilon naught. Therefore, electric field strength on the surface is given by 1 by 2 pi epsilon naught L Q by R. So this is maximum. It value constant at every point on the surface of the cylinder. Okay. Now, so here the third case is the point P3. Here I am taking this. This is the point P3. Right, sir? The point P3 is inside of the cylinder, which is at the distance R1 from the axis of the cylinder. Here it is denoted. From axis to the point P3, the distance is R1, sir. To find the electric field strength at this point, again, I am assuming this brown color cylindrical surface. So here this surface is passing through the point P3, or in other words, the point P3 lies on the surface of the inner cylinder. Okay. So now to calculate the field strength at this point, again I am assuming small surface area element. This is denoted with the brinjal color. The direction of ds bar same, radially outwards or normally outwards. The direction of electric field strength at that point same, radially outwards, that is denoted with the blue color. And E bar ds bar in the same direction. Then the flux through this small area element E bar dot ds bar d phi, that equal you will get E into ds, same concept. So whatever we discussed for external point on the surface, for internal point, here d phi equal to E into ds. Okay, of course, here electric field strength magnitude may be different. Electric field strength magnitude here, that is different, right? E into ds. Now the total flux through this entire inner cylindrical surface, inner cylindrical Gaussian surface is given by, we should integrate this one, phi equal integral of d phi, right sir? Here also same concept. Uh, the flux through the right circular end 0, flux through the left circular end 0. Only the net flux is contributed by the curved surface. In three cases, for external point, for on the surface, for internal point, the net flux is contributed only through the curved surface. The flux through the circular region 0 for both left and right hand. So that is we are calculating here, right? Now let us go for mathematical part. Right, sir. So here the total flux through the entire cylindrical inner Gaussian surface is equal surface integral d phi, that equals surface integral EDS. Since the electric field strength at every point on the surface of the inner cylindrical surface is constant, here E written outside into surface integral of ds. But surface integral of ds is equal to what? That is the total surface area, the total curved surface area of the inner cylinder. So that is written here 2 pi r1l. So only the difference is, what is the difference? Only the difference. In the previous case, we substituted here capital R. For external point here, we substituted small r. Since the internal point is at the distance r1 from the axis, here we substituted r1. So therefore, the total flux through the inner cylindrical Gaussian surface E into 2 pi r1l. But according to the Gauss law, this flux should be equal to 1 by epsilon naught times to the charge enclosed by that inner cylindrical Gaussian surface. So here the charge enclosed by the inner cylindrical surface is, we are saying Q1. Okay, Q1. But Q1 is equal to how we are writing? Here the non-conducting cylinder is uniformly charged with charge density rho. Rho is nothing but charge by volume. So rho equal to charge Q1 by the volume of the inner cylinder pi r1 square L. Okay. So now equating these two, then we get E into 2 pi r1 L equal to Q1 by epsilon naught, right? So E into 2 pi r1 L equal to, right side we substituted Q1 equal to rho volume charge density into volume of the inner cylinder pi r1 square L. The volume of the cylinder formula pi r square L. According to that, since the inner cylinder having the radius r1 and length L, then that volume is equal to pi r1 square L. So rho into pi r1 square L gives the charge distributed over the inner cylindrical surface, right sir, by epsilon naught. Then 2 pi cancel, 1 r1 cancel, L cancel both sides. Then E inside equal to rho r1 by 2 epsilon naught. Here epsilon naught is permittivity of free space, rho volume charge density. It is also constant, epsilon naught is also constant. Why rho is constant? We started the discussion that we consider a non-conducting cylinder with charge Q and uniformly charged density rho. So the non-conducting cylinder is uniformly charged with the charge density rho. So that means what? At every point throughout the volume of the non-conducting cylinder, the volume charge density, that is nothing but the charge per unit volume at every point rho is constant. Here rho constant, epsilon not constant. Then E inside depends upon what? That depends on R1. So E inside directly proportional to R1. So that means what? The electric field strength at an internal point is directly proportional to the distance of that point from the axis of the cylinder. So from axis to surface, the field strength increases linearly, E directly proportional to R1. Okay, so that is you can understand from this graph, sir. So here finally what we got, the field strength for external point or outside point 1 by 2 pi epsilon naught L small q by R. On the surface 1 by 2 pi epsilon naught L small q by capital R. Electric field strength inside point rho R1 by 2 epsilon naught. Here E inside directly proportional to R1. Okay, so on the axis, if you consider the point on the axis of the cylinder, then R1 equal to 0. So substituting that, you will get E inside equal to 0. Therefore, the field strength on the axis of the cylinder is 0. And as we move from axis to the surface up to the yellow line, the field strength linearly increasing. It is directly proportional to R1. So field strength exists maximum on the surface of this non-conducting cylinder. If you move further for the external point with increasing the distance, then E again decreases. Here E inversely proportional to R. So for the external point, field strength inversely proportional to R. For internal point, E inside proportional to R1. So that can be explained graphically from this. Here the graph is drawn between electric field strength and the distance of the point from the axis of the cylinder. At the point which lies on the axis of the cylinder, here field strength is 0. As we move from axis to the surface, here field strength increasing linearly, so we got straight line up to the surface, up to this yellow line. Their field strength is maximum, that value is constant at every point on this surface, this yellow line. And for beyond that, if you move further away from that surface of the cylinder, again the field strength is decreasing. Therefore, we are getting the curve here. Here E inversely proportional to R. Okay. So this is the electric field strength finding by using the symmetry of charge distribution by constructing the Gaussian cylindrical surface at 3 different points. So one is external point P1, the second one on the surface point, the third one internal point P3. Okay. So in this way, we can simply derive the expressions for the electric field strength by using the Gauss law, both for linear charge distribution, surface charge distribution, and volume charge distribution, sir. Okay, under volume charge distribution, we have seen the two cases. One is spherical charge distribution, the second one cylindrical charge distribution. Under spherical charge distribution, in the last class we discussed about uniformly charged conducting sphere, uniformly charged non-conducting sphere. Here we discussed uniformly charged non-conducting cylinder, and also you can discuss the same concept in the case of uniformly charged conducting cylinder also. Of course, it is not in our syllabus. That's why only I limited my discussion to this one. Okay. So with this explanation, in the case of uniformly charged distribution, okay, uniformly charged distribution for uniformly charged conducting sphere, non-conducting sphere, for internal point there we got E inside equal to rho